In this video, we'll talk about how to find the volume of three-dimensional shapes using calculus and integrals. So we know how to find the volumes of solids. So solids are three-dimensional shapes with equal cross sections. So where the cross sections stay the same kind of throughout the shape. So let's draw some examples. So one example is if I have a cylinder. Okay, so I have this circular base, and then I draw down, and then we have that circular base at the bottom, and I'll draw a dash, 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 dash at the back. Okay, so this is the radius of the base, and this is going to be the height of the cylinder. So when I talk about cross sections, if I were to slice this cylinder with a horizontal line, like with a horizontal slice, we would get a shape like this. So this is the cross section, and that cross section also has this circular shape. Okay, and we know that the volume of a cylinder is pi r squared times h. I can write this more generally. The pi r squared is the area of the base. So I can write this as the area of the base times the height. Okay, and we'll see that that formula shows up a bunch for similar shapes. So if I draw a rectangular box, so if I have a rectangular front, now let's make it 3D. So I'll draw diagonal lines to show depth, and I'll connect these. Let me draw a dashed line for the one that I can't see. Some dashed lines here, dashed lines here. And for the dimensions, let me call this x, and this one y, this vertical one h. The volume of a rectangular box like this is x times y times h. And the x times y, I could again just write it as the area of the base, because the base here is that rectangle, and its area is just x times y, and then times h. Okay, and if I were to slice this rectangular box with a horizontal plane, we would get a shape like this, which is a rectangle. So no matter how high up or down I slice it, we have that same cross-sectional shape. Okay, so we could even have something more general and curvy of a shape. So let's say I have a shape that has something like this as the base. And I'm going to call this A for the base. Okay, and I'm going to draw and make this look 3D. So I'm going to draw up at a bunch of points. This is some distance that's going to represent the height, some distance for the height, some distance that's going to stay the same throughout. Okay, and then for the back, maybe I won't be able to see these once I connect the top, so put dash, dash, dash. Got to make it the same height throughout. Okay, now I'm going to connect those tops. Okay, and connect them in such a way that I get the same sort of shape that I had for the bottom. Okay, that's going to look something like this. Something like this. Something like this, something like this. Okay, so we have this shape. All right, and this vertical distance, this is the height. And even for a shape like this, its volume is just going to be the area of the base. The area of the base times that vertical height. Okay, because no matter how high up or low I go, when I look at these cross sections, they maintain that same shape that has this constant area. Okay, so our goal in this section is going to be to find the volume of three-dimensional solids where the cross sections may change in size, but those end faces, so either the top and the bottom, or maybe they'll be on the left and the right, those end faces are parallel to each other and flat. Let me draw a picture. Okay, so in this picture, I'm going to have one of these sort of end faces. Maybe it's kind of curvy like that. And then, I'm going to draw what it looks like. Maybe it looks something like this. And from the bottom, maybe it looks something like this, and then it extends. And then at this other end, there will be some face. And again, maybe it's curvy. And then the back side, maybe I can't see just from my vantage point. Okay, so I want to be able to find the volume of a solid like this. So let me draw some of the other cross sections. So maybe somewhere here, if I draw a cross section, some part of it I'll be able to see. And then the back part, dash, 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 I won't be able to see. Let's draw one or two more. Here's the front. Here's the back, which I can't see. And then here's the front. Here's the back, which I can't see. Okay, so these cross-section shapes are, these curves. Okay, so I want to be able to find the volume of a shape like this. So what I'm going to do is I'm going to set up some axes. So maybe I'll call this the x-axis. And maybe I'll call this the y-axis. So the way that I have my axes oriented, these end faces, the ones that are parallel and flat, there's one over here, and there's one over here. Those are both parallel to each other, and they're parallel to one of my axes. In my picture, they're parallel to the y-axis. All right, so now what I'm going to do is, let's say that at this left end, I'm going to pick one point on this end, and I'm going to call that coordinate A. So if that end face is indeed parallel to the y-axis, every single point on that should have the same x-coordinate. And then similarly, if I were to take some point on this end face, I'm going to call this x-coordinate B. All right, and now what I'm going to do is I'm going to split up this interval into subintervals. So I'll do some tick marks, splitting it up into subintervals. Okay, and each of those subintervals, let me start to label these. Let me call this one x0, this one x1, this one x2, and then somewhere down the road, we're going to have some arbitrary one, which I'm going to call x subscript I. And what I'm going to do in this ith subinterval, I'm going to draw a 3D version of kind of like an approximating rectangle. So this is going to be a 3D shape now. So what I'm going to do is, at this x sub I point, I'm going to look at, this bottom point on my solid. I'm going to look at this top point on the solid at that same x value. And then I'm going to draw that cross section. So maybe the cross section on the front looks something like this. The back, maybe I won't be able to see. And then I'm going to make it look 3D. So it's going to have some thickness. It'll extend across my subinterval. And over here, it'll extend across the subinterval. And then this part over here, will come down. And then there'll be a back part. So we're making almost this like cylinder-esque shape, but it's not a circular cylinder. These bases are just some curved shapes here. Okay, so I am first going to try to find the volume of that. I'm going to call that the ith slab. So the slab is just a term I'm going to use to refer to this 3D shape. I'm going to call that a slab. So for the volume of that, I'll be able to find it using this formula for volume when the bases had the exact same size and sort of the whole way through or the whole way up, the cross section had the same shape. Because that's what this purple region looks like. The bases have the same shape. And if I were to sort of slice it vertically anywhere, my cross section would have the exact same shape. So that volume would just be the area of the cross section. And then times sort of this height, and this height, well, it's kind of sideways. So the height is going in the x direction, and it's really small, so I'm going to call that delta x. So it's area of the cross section delta x. Okay, so what I'm going to try to do now is, for the area of the cross section, I'm going to try to find a formula for that, and I'm going to call it a, and I'll be plugging in this x value into it. So I'll have a of x sub I, and then times that delta x. So the a of x sub I will come from an area function that we'll try to write depending on the problem and the information it gives me about the shape. Okay, so first, let's write down the approximate volume. So we're going to just add up the volumes of those slices. So for the first, or those slabs, for the first one, I'd have the area of x1, the first cross-section area, times delta x, that thickness that represents the height, and then plus the next volume, which is going to be the area of the next cross-section, area of x2, times delta x, that's that height. And I keep going like this, plus dot dot dot, plus the area of the last cross-section, x sub n, times delta x. All right, and I can put this in sigma notation as the sum from I equals 1 to n, a of x sub I, Okay, and then times delta x. And I can see those are going to be the same because if I plug in these values like 1 and 2 and 3 up to n in for the I get exactly the expression that we had above. Okay, so this is my approximate volume. We're adding up n volumes. If I want the exact volume, we are going to need to take a limit as n goes to infinity. The limit as n goes to infinity of the sum from I equals 1 to n of a of x sub I delta x. And as we've seen before with limits of Riemann sums, I can write this as a definite integral. My limits of integration depend on the variable x here. So the smallest it got was a, the biggest it got was b. The delta x becomes a dx in my formula. And then the x sub I change to the variable x. So we'll get a of x. All right, so I'm going to put a box around this. This is going to be our formula to get the exact volume. We'll need to get an area formula for a cross-section and then integrate that from A to B. And these numbers will sort of depend on how I set up my axes and where does my variable go from. Okay, I also want to note that we could also write the volume with a dy integral. It just depends on, so which one I use depends on how we align our solid with the axes in the picture that we set up. So we'll see an example of that in the next video. In terms of our goals, we finished goal 1. We've derived a formula involving integrals for the volume of a solid.